Let's just get started. Yeah. Kyle, do you have any questions about these computations that we were doing today for today's homework?
I don't think so. The inner product stuff is pretty easy.
Okay.
This question
Inner product stuff is easy. Okay. Well, let's get into the. We want to head on toward the Hilbert adjoint operator, which is kind of good stuff. We're told it's very applied. But we have to know a little bit more. And if you really want to get into all that, the generating functions and stuff for the Legendre polynomials and whatnot, let me know. It might actually be a pretty good project just to take that one section and do all the problems. So that would be a project, for example. Yeah, I think I mentioned this as an optional project instead of doing the homework in Chapter 9. Toward the end of the course, you could do all the problems in 3.7. It looks like it would be a good project.
Yeah, it'd be a big project.
So, but it's, finite. Because there aren't that many problems. Okay. Okay.
In computer science, we have a thing called infinite loops. So I don't know if it's.
Okay. Let's get started. It looks like it's going to be a little bit late for people today. People are getting behind on the homework, so they're not showing up on the day the homework is due. That kind of stuff.
Yeah.
I think I'm just going to have to make it due Mondays from now on. What do you think?
Well, for myself, I usually have time to work on homework on the weekend.
I usually do it during the week, so this is a good time for me. And I have other homework due on Monday, so.
You don't want to have it
I don't
changed.
really want to have it changed.
Okay. Well, it looks like the other people are pretty much just going to turn it in on Monday anyway.
On the following Monday?
Yeah.
Yes, sometimes it's a little harder because we haven't covered all the material for the weekend and
Yeah.
working on the homework. But it's usually not that.
So you claim that you won't have any time to fix it, but
Yeah. It wouldn't help me out, but.
okay. All right. Well, we'll discuss it when we get more people here next time, I guess. It's pretty much become like independent study. For some people, they're just getting it done. Yeah, that's pretty much what's happening. So I can't really blame them on the first time through this course. I'd like to have a little bit more discipline, but.
What if you give us extra credit for turning it in?
Well, I could, yeah. Oh, it wouldn't help me. Okay, so I think I'm just going to go ahead if there aren't any questions. Like I said, I was going to talk about the Weierstrass approximation theorem when we get to it in Chapter 4. Right now, I'm just wanting to finish Chapter 3.
Are we doing any more with Zorn's lemma, or are we done?
We will start with that when we start the new chapter.
Okay.
But I would like to finish this chapter and give you the test.
Oh, right.
And then right after spring break, we'll do the Chapter 4. We'll start with it then. Oh, we do have a quorum now. We have enough people to get going. Okay, so here's your homework, Travis. Okay. So let's talk about, I guess I'm just going to go on to the next topic. I've pretty much skipped 3.7 for the rest of the work. You can go through all those calculations of orthonormal systems sometime either in a project. I mentioned that, Travis, if somebody wanted to do a project, just do all the problems in section 3.7 for a couple's weeks worth of homework. Okay. So we're going to go on to section 3.8, and that's the Riesz representation. It's not very difficult.
We have a new homework assignment online.
Yes, it is. It's the rest of Chapter 3, 3.8, 3.9, and 3.10. And there's a couple interesting problems in there. So what I want to get is to the adjoint operator if I can today, so you can actually do something with it. We'll see. But the basic tool is the Riesz representation theorem. It's a very simple idea. So let me just give you an example here. Let me give you some notes. You can you can read my handwriting about it. In case you get any questions. So let's have an example. Let's just take the Hilbert space H equals little L2. Remember when we were doing dual spaces? We were doing dual spaces and we wondered what the linear functionals looked like. Well, what do the linear functions look like on little L2? What do you think? What's the inner product? First, well, what did we have before? Remember, if we had a basis, we said, oh, okay, it's pretty much linear combinations of, it was just like, if Z equals A to 1, A to 2, and so on, so this is the question, what are the linear functionals on H equals little L2 look like? If Z equals A to 1, A to 2 is in this little L2, and X is also, I'll put it C1, C2, is also in little L2. Now let's fix Z. Z fixed. Z fixed, and then X is variable. Okay, so let's take X variable. Then I can define the following. The inner product, the good old inner product between X and Z, which on little L2 is simply defined, is equal to summation C K Z K bar. A to K. Sorry, A to K bar. K goes from 1 to infinity. That's the definition of the inner product in little L2. This defines, I could call this f of x, then f of x equals this, defines a linear functional. Okay, let's just check that. Obviously it's linear, okay? Let's check that. F of x1 plus x2, or let's do alpha 1 x1. Do it all in one computation. Alpha 1 x1 plus alpha 2 x2 is equal to, put the alpha 1 x1 plus alpha 2 x2 on the left side of this inner product. And we obtain, by linearity of the inner product, that's just simply alpha 1 x1 z plus alpha 2 x2 z equals alpha 1 f of x1 plus alpha 2 f of x2. So a very simple computation using the linearity on the left side of the inner product. Okay. So that's why we didn't define it f of x equals z into x. We did x into z, so we get the linearity and not a conjugate linearity. Okay. Okay, so that's linear. Is it bounded? Because what are the bounded linear functionals is what I meant here. I want bounded ones. I want the actual dual, not the algebraic dual. The algebraic dual, remember, is just the linear functions, whatever, bounded or not. I want the bounded ones. All right, what are the bounded linear functionals?
That's alpha 2, f of x2, right?
Yes. Very good. Okay, so what is that bounded? Is this expression bounded as a function of x? What do you think? How would you get that? I need is f bounded? What do I need? That means, let's recall what that means. Is f of x less than or equal to some norm of f times the norm of x? Okay? What do you think? For all x. and some norm finite. Well, I should put C here. I'll put C here, and some C less than 0, C less than infinity. So I'll just put the C instead of the norm. The norm F is the smallest C that works. And I want to know, is there just any C that is any good? So there's the question.
James lemma, or I don't have the book on.
It's called an inequality.
I can't think of the. Yeah, it's the main one from like 2 sections ago. What's the guy's name? Bessel, yeah.
No, it's not the right one.
No, you wouldn't use that to argue that each of the f of x1 and f2 are somehow bounded.
Oh, I see. Well, that's the norm of that's. See, these are complex numbers, so there's no lots of dimensions for these things.
Yeah, right. You wouldn't want to call those e and all that.
Yeah. So what else would work, though? I mean, what other good thing? I want to make this expression right here. One of the terms should be a norm x, and then I need something else, and an inequality. So what am I? And I just want to put absolute value of xz. Okay, f of x equals absolute value of xz. Okay, very good. Less than or equal to norm x, norm z by Cauchy-Schwarz inequality. Okay. Therefore, indeed, c, little c equals norm z, which is finite, works. Okay, in the definition of boundedness. Okay. In fact, you can actually obtain the norm of that linear functional. So we can actually not only show that it's bounded, but we can actually find the norm. What is the norm? Now, it would be so z is this fixed thing. Norm of z is a c. What is the smallest possible c you can get? I claim it also is just this norm of z, because I can make this linear functional come up to the right hand side with equality in the Cauchy-Schwarz inequality always by choosing the vectors parallel. So I have this z fixed. Call it z naught if you want, but I want to choose my x so that x is parallel to z. We'll just choose x equal to z. All right. So now f of z is equal to the inner product of z with z, which is just the norm of z squared, which is take x equal to z. All right, which is the norm of x times the norm of z. So I have equality. All right. So norm of z. So what I have here is this implies that the norm of f is less than or equal to the norm of z. Okay, because the norm of z worked as the bound c in the norm inequality. All right. And now I have that norm of f is greater than or equal to z. Therefore, since f of z divided by the norm of z is equal to the norm of z, this implies that the norm of f is greater than or equal to z. Therefore, the norm of f is equal to the norm of z. Okay. So I have this particular thing. So I just use the inner product to define a linear functional, and I actually easily obtain that it is linear. I easily obtain its norm, and that looks pretty good. Now, the z is unique. In other words, each z defines a different linear functional. Let's check that. Unicity of z. if f sub z equals the inner product of z with x with, if I define, this is going to work. Note, if we put f sub z of x equals to xz, and if f sub z is equal to f sub w as linear functionals, then I claim that z equals to w. That's quite easy. Then z equals w. Let's check that. Check. Check this statement of unicity of the representation of f sub z. Okay. Let's check that. If I've got xz equal to xw for all x in little L2, I'm just working with the example right now, even though it's not important. As you can see, I haven't used any properties of little L2 yet, except the formula, just to make it. Okay, I haven't used anything about little L2. Just that I had an inner product, so I faked you, okay, out just to make it more explicit, okay? So they have this one formula right here. I have never used this, okay? Just made it clear that what you get is some kind of linear combination, okay, of the x's. That was that idea of what a linear functional should always look like. Some linear function of the x's, all right? So we're just going to, for all x in L2, this implies then that x z minus w equal to 0 for all x. And then I'll just take x equal to z minus w, since all these are vectors in my Hilbert space, which implies that z minus w equals to 0, which implies that norm of z minus w squared is equal to 0, which implies, of course, that z equals to w. So there's only there's not two different ways to write the same linear functional in this way. The only question is whether I can write any bounded linear functional in this way. That's the question. If f is a bounded linear functional, can it be written in this way? So there are three questions. Can it be done? Is it unique? If it is done, we've settled that. And three, what's the norm of it? If it's written this way, we've settled that. So we've settled two of the three questions in a general Hilbert space, because I've used nothing about little L2. Okay. So let's just state the Riesz representation theorem then. And let's go ahead and prove the last part. Does every bounded linear functional have to have one of this form? Will I always get such a representation if I do have a bounded linear function? And the answer is yes. But we'll see. This is kind of nice. It's not very difficult now that we have what we have. 3.8-1 is the Riesz representation, or theorem, the basic one. He's got it. Let H be a Hilbert space. And F, a bounded linear functional. On H. Then there exists a unique Z in H such that f of x is equal to the inner product from H of x with Z x on the left side, z on the right side, for all x in H. And for this z, the norm of f is equal to the norm of z. So the z that I choose, of course, would have to be such that the norm of z was equal to the norm of f. That's necessary, but we've already established whenever you have this representation. So the question is, and the uniqueness we've already established. So I've checked this part, and this part I've checked already. Now I need to find this. Okay? Is it always there? Certainly it always does define one that's unique with z, but we've already checked that it does define one. But does any linear functional then have that form? I mean, if you just take a linear functional out of the hat, is it going to have that form? Will that cover all of them, in other words? So let's have some discussion about that. First, recall that if that the null space of F is closed in H. Check that. Let's check that. Let's just do the real quick proof of it. It's the same thing. Here's where I'm going to use boundedness of F. This is where I'm actually, the only time I'm going to use it is right here. Is boundedness of F. Then this implies that F is continuous. Right? So, because it's linear, by linearity and boundedness, I'm using linearity. I'm going to use linearity a bunch. But boundedness, by linearity and boundedness, thus, if xn goes to x, where xn is in the null space, okay, and x is in H, then f of xn goes to f of x, okay, by continuity, but f of xn is equal to 0 for every n. Therefore, f of x is equal to 0. QED, all right, for that little parenthetical remark. Okay? So you have is closed. All right. So therefore you have the situation of the projection theorem, that you have a closed subspace of a Hilbert space, therefore you have the direct sum. Therefore H is the direct sum of NF and its orthogonal complement. Okay. Remember, the null space is the set of all x that get mapped to 0. So, well, if you don't have the 0 functional, then there has to be something that doesn't get mapped to 0, right? So assume that f is not equal to the 0 linear functional. Otherwise, it's trivial. It trivially has a representation of x inner product to 0. Okay? That's the trivial case. So assume that f is not the 0 linear functional. Then NF is a proper subspace of H. So that means that the orthogonal complement has to be non-zero. So NF orthogonal complement is not equal to the 0 space. Otherwise, you wouldn't get the whole Hilbert space back again. There has to be something. Okay? In other words, there's got to be some element that is not in the null space. So then when I project onto the null space, I get a non-zero residual. There's a null space. It's just like a plane. Okay? There's a null space of F. here's something that didn't get mapped to 0. Okay, so I project on there. Okay. Now, let's see what we're going to call it. Let's call the element that doesn't get sent to 0. So there exists Z naught. There exists Z naught unequal to 0, Z naught in the orthogonal complement. Okay? Here's Z naught. Okay? Okay, so what am I going to do with that? Well, now, here's the trick. The trick is to write a general element that is in the null space in terms of any x. So for any x in the Hilbert space, I'm going to generate an element of the null space. The trick is this. For every x in H, write an element V in the null space. Come up with an element. V equals V sub x, actually. V sub x in the null space. Defined by V sub x. Let's see. The trick is that it's f of x is just a complex number, right? Times z naught minus f of z naught times x. Okay. So we're using the fact that f is a complex number, and that will always get mapped to 0 because when I apply f being linear, I'm going to get f of x, f of z naught, f of z naught, f of x. Apply f, right? F of v, check. Indeed. F of vx is equal to. So this is something, it's hard to visualize in the picture, but it's easy to handle algebraically. It's f of x z naught minus f of z naught times x. Now, using the linearity here, I just pull out the constant, which is f of x, f of z naught, minus f of z naught, f of x. Using the commutative, the fact that the complex numbers are commutative, okay, in multiplication, and so that gives me 0. So I do have a vector, all right, and it's non-zero. I mean, take just anything x which is not parallel to z naught, all right. Then this is a non-zero vector. I have a bunch of non-zero vectors, so I've identified a bunch of vectors in the null space. There's a lot of things in the null space. Okay. Null space is going to have codimension 1 anyway. Okay. So practically everything is in the null space. And everything, unless I take x parallel to z naught, this is a non-zero thing. All right? So in other words, if I take x equal to z naught, then it does come up to be 0. V is 0. All right? So I pretty much have written out the whole null space here. Okay, in this way. And now, in fact, all I got to do is probably just take the orthogonal projection of x onto the null space. Is probably just all we're doing here. How would I take the orthogonal projection of x onto the null space? If you want to think about it that way, how would I do it? Here I'm going out on a little limb because I didn't prepare this. If I took a vector x and I projected it onto the null space, what would I get? I'd have the condition that if I wanted to have some vector v in here, then I would have that x minus v should be perpendicular to v. and I should have that that f of v equal to 0. Okay, so and well, okay. Another one thing is that I should have that this should be that I should have that x minus v should be parallel to z naught. So x minus v should equal some constant alpha times z naught, right? Because z naught was what I said was the normal vector here. Okay, normal vector. So I should have x minus v equal alpha z naught, and then I should have that. So I get that v equals alpha z naught, so minus x, and then I think the only thing is that I put in an extra factor, okay? And so I could have divided this by f of z naught as well, okay? And so if I divide by f of z naught, I get the same kind of expression, okay? So equals alpha z naught minus f of z naught x alpha prime divided by f of z naught. Okay, so you can see basically how the v would come, how somebody would come up with the v. It's not that bad. You would have to do something like that. Okay, and this is just a nice, pretty way to write it out. Okay, where it makes it obvious that f of v has got to be 0. So it's not like some kind of mystery once you get the z naught going. Okay? Think about it. Just if I was going to project something from an R3 onto a plane in R2, if I have a normal vector, I have the normal to the plane, then I can actually find the projection pretty easily, right? Okay. So this was not that difficult to find. So now I claim that this is going to do the job. So because now I claim I can, since this is there, then I have this v. Okay. It is the null space. Therefore, it's orthogonal to z naught. Okay. Use that v is perpendicular to z naught, and see then that f of x z naught minus f of z naught x inner product with z naught is equal to 0. And when you write that down, then you simply f of x simply pops out. Okay, so you get f of x. You get a formula for f of x. F of x z naught minus f of z naught x z naught equals to 0. So that gives that f of x is equal to x z naught times f of z naught divided by the norm of z naught squared. And so now I can put everything inside if you want and write this as x times f of z naught bar z naught over z naught squared. And so this is my z. Okay, this is my z. I have to get the right size of it anyway. And that is it. It has to involve the f because the norm of this thing has to be the norm of f. So it involves the f as kind of a parameter. Okay? In the definition of my z. That's it. So there is some representation. Okay, so for every x in H. Okay, that's the end of the proof. You have established that indeed that any linear function must be written as an inner product. Doesn't seem too bad. Okay. It's going to have some useful consequences. I mean, if you know, most of the stuff you're going to see in this last half of the chapter, you say, well, that's kind of obvious that you could do this, and so on and so forth. But not obvious until you've seen it, maybe. It's like, are you sure? We better go through this. The computations are not terribly difficult, you can see. So what are we going to do after that? Well, we want to get something called the adjoint operator. Okay. So you remember about symmetric matrices? You remember anything about symmetric matrices?
Definition.
Yeah, what's a symmetric matrix? So, symmetric matrices. It would be something that, A11, A12, A13. Let's just do the 3 by 3 case. A1 there. Well, I'll just run it out as ABC. That's easier. ABC, B, D, E, E. What's this one? I'm sorry. It is a C, E. C, E.
Oh.
Well, yeah, that's good. E and then E on the second C right there should be E down below, right above your. That should be an E and then E, right?
B, D, what? Oh, E. Sorry about that. C, E, F. There we go. Okay. Save the day. Okay, so there's a symmetric matrix. Okay. 3 by 3 symmetric matrix. Okay. So what's the property of this? That is, if I take x1, x2, x3, and just matrix multiplication, A, B, C, B, D, E, C, E, F, and then I take y1, y2, y3. This is just for x equals x1, x2, x3, and y equals y1, y2, y3. Good old elements of R3. Okay. So the real case. Then that's the same as if I switch the y and the x. This is equal to the transpose of this expression. This is equal to y1, y2, y3, A, B, C, B, D, E, C, E, F, x1, x2, x3. Okay? Now that's not true for a general matrix. Right? So I can switch these. So what you have is that you have X transpose A Y, okay, transpose, how you would prove it, is that this by transpose is Y transpose A transpose Y. We're taking the transpose in the reverse because X transpose transpose, okay, equals Y transpose A transpose X. Okay, this is the proof. Okay, all right. But once you know that the transpose of a product is the product of transposes in the reverse order, which is another lemma, okay, from way back when. Okay, and of course, A transpose was equal to A by the way we chose it. Okay. So, now also, what is a Hermitian matrix? That's one where you're taking complex values. So now I'm going to work with C3. So what do I have to do? So now I'm going to take A equals to, transpose and complex conjugate has got to be the same. So A star. So now I'm going to take A, B, C, start the same way. But now B conjugate, D, E, C conjugate, E conjugate. F. Okay. Or you can use star if you want, but star means when I'm going to star equals conjugate transpose. So for a complex number, star and bar are the same. Okay. Star and bar are the same for a single complex number, but then for a matrix, of course, it's a little bit different because you have the transpose business. Okay. So now if I take x and y in C3. Okay, then I've got a different story. Okay, so I better go on to the next page so that I don't confuse everyone. This is the real case. All right. But now I'm going to do a complex case. So what do you have now? You have that. You also have the rule that the conjugate transpose of a product is the product of conjugate transposes in reverse order. So now if I take x, well, yeah, I guess let's just take x again now. X equals x1, x2, x3, but now x1, x2, x3 are complex numbers. Then what you have is that x transpose a y. That's still a transpose. Okay. And now if I take the conjugate transpose of that, then I obtain y conjugate, okay, transpose a star x transpose, well, I'll just put x bar, okay? I'm sorry, I started with the wrong thing. I wanted to do this. I want to put a bar here. So now I get to put a double bar on here is equal to y transpose a star x bar, okay? Which would be equal to y transpose a x bar, okay? If I assume the a is equal to a star.
Isn't that forced, like, in this example, like the A, D, and F to be real? Or zero? Well, I guess it's zero.
No, they wouldn't have to be real. The eigenvalues have to be real.
Well, when you do the
oh, I'm sorry. Conjugate transpose. Yeah, conjugate transpose. So the A. Yeah. So do they have to be real? Yeah. They have to be their own conjugates. So they have to be real. Yeah. Diagonal have to be real. Yeah. So these are A, D, and F. Well, forces A, D, and F. Yeah. So I need A, D, and F in the reals. Okay? So that would be the general formula. You're right.
So if
it's a little bit harder to write down, as you pointed out. Thank you. Thank you very much, Travis.
If they are, then it just doesn't.
It can't be. Yeah. So it has to be A equals A star is the condition. So it'd be easier to write down A11, A12, and so on, and say then A equals A star. But if you actually try to write it down in terms of parameters like this, then you have to assume that A, D, and F are reals. Exactly. So it's a little bit harder to write it down in this quote unquote simpler form. Okay. I'm insisting that A equals A star. This is the Hermitian case. That's a definition of a Hermitian matrix. And the point is that that's for the 3x3 case. That's equivalent to well, that implies this. Okay? Okay. Is that clear now? This is the definition. And in the 3x3 case, that implies this form. Okay. I didn't write this out in the notes, but it was kind of material that everybody needed to know or recall. Okay? So what I have is these quadratic forms, so-called. Okay, but what is this? This is simply X inner product AY. Excuse me, AX. Let's see, is that right? What is that? Yeah. What is that? I like to think it this way. Yeah. So, well, I have, in general, what I have is this. Okay, so what I have in general is this. This is general formula. Okay, and this is the general formula here. This is by symmetry. Okay, so this is the general formula here. Okay. So what is this? What is this in terms of inner product? What is the inner product? So maybe I don't have these things written out the way I want it. The inner product. What is the inner product in terms of in Cn? Inner product in Cn is simply equal to of x and y. Okay, is equal to xi y or yj bar, right?
Yeah.
Okay, which is equal to x transpose y bar transpose. Excuse me, y bar. If I think of these as column vectors, okay, where regarding x and y as column vectors. Okay. Okay. So everybody have the general formula, just using transpose of product as a product of transposes in reverse order. And then in the symmetric case, I get that the original quadratic form is equal to the quadratic form with the x and the y switched. Okay. Then I have the general formula for the conjugate transpose of this quadratic form. All right. With some kind of quadratic form involving x's and y's, so there's this conjugate in there. All right. So it's not a real quadratic form. It's a complex quadratic form. And then I get, by taking the conjugate transpose in reverse order, I get a different quadratic form with a star in place of a, and the y and the x are switched. Okay, and then the Hermitian case, this form is really just the same as the original one, with the same matrix, only with the y and the x are switched. Okay? So what is the inner product in Cn? It comes out x transpose y bar, right? So can I write this quadratic form in terms of the inner product? Let's see, how does that work? I guess, yeah, it's kind of, maybe we didn't have it nicely done here. Let's see if I made a mistake. Probably should have prepared this stupid thing. Okay. Yes. Okay. Unfortunately, yes. Okay. Well, so now I have to. What I have is that, unfortunately, this one, which is the one I want to focus on, x transpose a y conjugate like that, even though it works out nicely in this formula, that's going to be written as a transpose x transpose y bar like that. Okay. And if I rewrite that, then that is equal to y transpose a star x, which can be written as therefore a transpose y star. I'm sorry. Yeah. I said I could write it like this, right? Which is the same thing as a star. Okay. So, how can I get the, which is the same thing as a bar, therefore, y transpose x bar. Okay? So what I have is that, okay, that's correct, where a bar is the conjugate, because transpose has the conjugate again. Okay. Okay. So what I have is that, I guess what I'm trying to say here then is that if I now replace A transpose by something else called B, okay? If I now call B equals A transpose, so make a change of variables, call B equals A transpose, then I have that BX transpose Y bar, which is the inner product of BX and Y, is equal to what I said down here is the A bar Y transpose X bar, which is the same thing as B star Y transpose X bar, which is the same thing as B star Y inner product with X. Okay. Is that the way I wanted it? No. Maybe not.
Doesn't it move to the other side?
Yeah, it's supposed to move to the other side. Now, why did I mess it up? Well, yeah, this is the general formula. This is not, this is the general formula. Okay. Now the question is, if B is equal to B star, okay, then what happens? Okay. If it's self-adjoint, okay, this is the general formula. So I get to switch the X and the Y at the cost of the star. Okay. That's right. But now if I want to put what happens if I want to switch the sides on this thing? How do I switch sides? Which is the, maybe I made a mistake here. Maybe what I get is A bar, is that the same thing as B star? B star would be, what is B star? I'm sorry, I have a transpose wrong. I have a transpose wrong. This is not correct. You're right. This is, if I take the conjugate of both sides, right, I'll have B bar equals A star, right? So this is the conjugate transpose, so therefore I want to have B bar in here, right?
Yeah,
B bar. A B transpose. I need to a B transpose will be an A, and I need a B bar in here.
Now we get B star.
Well, no, that's a B bar Y, because this is the way we defined it.
Yeah.
Okay, there it is. Okay, now switch the sides. Equals, if I switch them, okay, take the conjugate of both sides, If I switch the two sides, you get the conjugate, right?
Right.
Well, let me see. This is confusing. I didn't do this well. Okay. So, what do I have? I have this is a formula. Okay. Which I interpreted in terms of B. I had this is equal to this. Okay. Which then if I write down in terms of B is BX, Y, okay, equal to B equals A transpose. So if I wanted that for B transpose equals A, and I put a bar, B star equals A bar. That's correct. Okay? So this was a star. Okay. So I get a B star Y X. Okay. So what I did is
So what do we want to do? I just want to switch them around.
did I make a mistake? When I did this, I went BXY. I was supposed to get BX transpose Y equals A bar Y. How did I get to A bar Y? Where do you get A bar Y from? That's what I said it was equal to. It was when I switched them. Okay. How did I get A bar? I should have gotten B bar. That was my problem. How can I do this thing? I need to... Oh, okay. I see. BXY was this. I said it was equal to A bar Y transpose X bar. Okay. And I was just rewriting then A bar in terms of B. A bar was equal to B star. That is correct. B star Y transpose B. That's right. B star Y transpose X bar. Okay, well it looks like this. Looks okay to me. Now what's the problem with that? I want it to be something else. Okay? I want to start with A transpose should equal B bar. Oh, I see what he did. He wrote in the same way. Okay. Yeah, see I'm switching the X and the Y. I'm switching the sides in what the X and the Y are as well. Okay, I don't want to do that. Okay. If I want to get if I want to get the other thing. So if I want to, what I do is conjugate and conjugate again. Okay. So if I take this and write this is B star Y transpose X bar, and I want to conjugate, and then if I flips the sides, that's the same thing as conjugation, right? So I want to conjugate that. And then conjugate it again. So I think it comes out this X B star Y. Let me check. Let me just check. Check this. This is equal to X. I mean, it's equal to this. If I switch, then I get a conjugate. This doesn't look right. I'm going to have to skip it. Fix it later.
Is it right up until then?
I don't know.
Okay.
I'm getting confused. I'm wasting too much time. I think that well, this part we got right. Okay? Okay, the inner product is correct. Representing the inner product, this is correct. Okay. What I said was, did I use A star equals H? No, I didn't. Now I said, if I... now how did I get this? Oh, I had a general formula. I had that A transpose X Y bar transpose is equal to something. Okay? But what was this coming in? This is just incorrect. Because somehow I was putting a transpose on that thing. Right? I was doing this operation. I'm not doing this operation down here. So this is where it fouled up right here. Okay? Okay. So if I'm just writing this out, somehow, how did I get the X bar in there? I can't unless I take a conjugate transpose. So I'm not doing a star operation here. All right? So, so what I want to say is, I have to put the star in somewhere. Okay? The star is equal to itself. So what it is, it's this thing starred. This is where it messed up. Okay? In other words, I have this star is equal to all this business. Okay? So, in other words, I have to start with an X transpose. Okay? Check this. So if I take A bar Y transpose X bar and then star it, okay, I get, in reverse order, this will be an X transpose. Then I'll get an A bar Y conjugate, okay, which will equal to, I'm sorry, this is, yeah, which is going to be, the conjugate doesn't reverse the product, X transpose A Y bar. Okay, so it looks like I had B equals A transpose, so this doesn't look quite right. So okay. So yeah, I understand what I did now, which is too bad. I messed up all that time. Used up the rest of the time. Okay. This is correct. All right. I want to show that if I want to rewrite a form, let's see when I'm going to do it. I want to rewrite it where it's where the B is on the Y instead. Okay? Okay. I want to rewrite it where the B is on the Y instead. So how will I do that? This is simply X transpose B transpose Y. So if I want to write it on the Y, I'm going to say Y bar. So if I want to write it on the Y, it's trivial to do so. All right? By putting X transpose B transpose Y bar, well, put a bar on here and put another bar on here and then put the bar on there. Okay? The order of the product is not changed by the conjugate. Okay? The double conjugate is itself is back again, so I get this is X transpose B bar transpose Y conjugate. Okay? So that's simply inner product X B star Y, because the conjugate defines the inner product. So I didn't need to do all that. I'm sorry. If I just want to show how the star matrix comes in terms of the inner product, if I keep the X and Y the same, okay, then on the same side, then I get this way. I guess what I was showing you before is when I flip the x and the y, I get the same quadratic form. Okay, in the Hermitian case, all right, when they equal A star. But if I want to just show an identity for the inner product bxy and then put the b on the other, somehow the b information on the other side, then it comes out like this. Okay, so the next theorem is to do this on a Hilbert space. Okay, how do you define the transpose? Excuse me, the adjoint. We want to have a theorem that allows us to take the adjoint. And unfortunately, I blew a lot of time on that, but hopefully this messing around will pay off in the future. So what I want to do is I want to define, given that T is an operator from a Hilbert space to a Hilbert space, actually I'm going to be able to take it from one Hilbert space to another Hilbert space. Bounded linear operator. Assume that you have one of these. Okay? And then I can always form the following expression. I better look at the notes this time so I won't get the sides wrong. You get the sides wrong on this thing and you really get messed up for a long time. You've got to be extremely careful. Okay. I can always define the following operator. I can define the following expression: h of x and y is equal to y into tx. Okay. I can always define that. That's a function of two variables, x and y. So here x is in h1 and y is in h2, and the inner product is the h2 inner product. So I have two Hilbert spaces, and the inner product is always going to be in the h2. Okay? Because y is in h2, x is in h1, tx gets to h2, so now I have something in h2, something in h2 here. Okay? I can always define that. It turns out now that we're going to have a representation theorem where I'm going to be able to represent this thing and switch the sides. So I'm going to be able to represent by another representation theorem for more complicated things called sesquilinear forms, which aren't really very complicated, and I'll have to talk about them next time. Sesquilinear form is going to allow me to represent this h of yx. I'm sorry, this is h of y and x. This is why I was pointing out you've got to be really careful with the two sides, h and y and x. It's going to allow me to write h and y and x. The representation theorem is 384, I believe. It's going to allow me to write h and y and x as some operator t star of y into x, where t star is some mapping from h2 back to h1. Okay? So therefore, I'm going to be able to have these two things equal. This is in the inner product is in h1. Okay. So now I'm going to have ytx equals t star y x. So what 33.8-4 is going to do is going to define this adjoint operator. That's the definition. So this is going to be a uniquely determined adjoint operator where the norm of t star is equal to the norm of t. So I have a bounded linear operator. T star is also going to be a bounded linear operator with this norm. And then we're going to want to reinterpret in terms of matrices when the time comes. But at this point, we just want to think about linear operators. And so this is going to be the adjoint. And self-adjoint is when T star equals T. That's just the definition. Okay. So I need this other representation theorem where it turns out this is going to be something called the Sesquilinear Form. Okay. It's going to be linear in one variable, conjugate linear in the other variable. Okay. And it's going to have a norm inequality a lot like an inner product. So in fact, an inner product itself is going to be such a Sesquilinear form. So the order of the variable is important. It's going to be linear on the left variable, conjugate linear on the right variable. So it's linear on the left side, conjugate linear on the right side. And that's going to be, so we're going to have a Riesz representation theorem for such forms like that instead of just having one variable, two variables. Okay? And so once we get it, then we're going to be able to write it out this way. Okay? Because what you're going to have is that any of this h of yx, if that is one of these Sesquilinear forms, I'm going to be able to write it in terms of inner product. Right? I'm going to be able to write it in terms of inner product with, if that's the conjugate linear part, then the x is going to be on the right side. And this is going to be some operator applied to y. Okay? So any Sesquilinear form is going to be written out like that. Okay? Instead of just a z into x to get the conjugate linear thing, I have to, since there's an extra variable here, I have to have, instead of having the z, I'm going to have a linear operator applied to y.
So what are we calling it? A Sesquilinear?
Sesquilinear.
Isn't that the 1.5 times linear?
Well, it's the bilinear form is when it's linear in both sides. Okay, and the real inner product case is called bilinear. I think sesqui has to do with the fact that it's linear and then conjugate linear. Yeah, so it's 1.5. 1.5 linear. It's almost bilinear, but not quite. Okay. Well, I'm sorry for messing that up with this business.
We all do it up there, you know. And
yeah, it occasionally happens. I always get messed up with these transposes and stars and stuff. I'm not very good with both sides of my brain.
It's always bad when
communicating.
it's up there, because it's harder up there than it is on paper somehow, I found.
Yeah. Well, you can see, I did something I hadn't prepared in the notes. I was just going to show this matrix.
Yeah.
I can show this stuff. But obviously I had a gap, okay, in what I was thinking about, because I was trying to switch the x and the y. That's how I thought I was supposed to do it. You weren't supposed to. Okay? Okay. So, all right. We'll come back to it. Thank you.